Hey everyone, thanks for joining. I'm Rishabh, an engineer with the Jetson product team, focusing primarily on robotics simulation. And in today's weekly live stream for Isaac Sim, we'll be looking at the ROS workflows which you can use with Isaac Sim. We'll basically be looking at the extensions, the Omnigraph nodes, Python scripts, and all the related components which you would be needing if you have any ROS packages or other components which you would want to integrate with Isaac Sim. So let me get started by presenting my screen. Just the layout here. Okay, so let's. I think the first thing which you need to keep in mind if you're using Isaac Sim is the best point for getting started and understanding what requirements your system needs in terms of the hardware and even in terms of like Ubuntu versions, Python versions, and all related things. The Isaac Sim documentation is the page to go to. So the link is right here. Let me paste that in the chat too. So talking about, yep, this is the link right here, which you should be looking at as your first starting point. And I'll quickly walk through the installation part as well in case people have had issues with that and just want to understand what's the best way to get started. So you can go to the system requirements and you'll find all the related specs which you would need in terms of running Isaac Sim. So this is and one issue which you might see if you use like Linux PPA drivers, we would certainly recommend that you use drivers installed from the .run method, and you should be able to find the the drivers corresponding to the Isaac Sim versions on the NVIDIA drivers website, and make sure you have the right versions installed because if you do install it from other sources or from other methods at runtime, we've seen errors popping up and they might get difficult to debug. So make sure that you follow the instructions in terms of getting started with Isaac Sim. You can run IsaacSim basically via two methods. So you can have it locally running on your workstation where you can download like the Omniverse launcher and you'll install a couple of dependencies with IsaacSim over there. And once you've done that, then you can just directly start IsaacSim by launching it from the OB launcher itself. And we'll be taking a look at this as well in terms of how we can go about it. The other way which you can actually get started with Isaac Sim is if you have a remote workstation, or maybe you're looking into cloud deployment strategies where you may be having an EC2 instance, for example, on AWS. So what you could do there instead is uh, you can use the Docker based workflow which we provide. So you can have the Isaac Sim Docker pulled in from NGC, and there are a couple of steps which you need to follow there as well in terms of making sure that either your workstation, which is a remote workstation, or your cloud instance has the right GPUs and the driver version installed. There's a CUDA toolkit dependency, and once you've done that, you just need to pull in the Docker container for Isaac Sim after you've logged into Docker. And once you've done that, by just running this command, you should now be able to run Isaac Sim. And via the Docker mode, you can run Sim headlessly and have a streaming client either locally or even that could be running on your remote workstation as well, which is now going to stream the GUI. So in case you're not running Isaac Sim headlessly, but you are wanting to understand what's happening through the GUI. Like you can run it headlessly, but you're adding some objects to the scene. Maybe you have a robot moving around. You want to make sure that the physics looks correct. So initially, it would make sense to have access to the GUI. And once you become a more advanced user, you can go into actually complete Python scripting, and you can have everything run headlessly. So that was a quick start in terms of understanding how you can install and use Isaac Sim. The next things which we'll be taking a look at is the ROS and ROS2 installations. So uh, you have support for IsaacSim on Ubuntu 20 and Ubuntu 22, and the default version with Ubuntu 20 is ROS2 Foxy, and with ROS 1 it is Noetic. And in case you are using a system which is based on Ubuntu 20, but you want to use the Humble bridge, for example, your entire software has been written across to Humble. So what you could do there is you have two options. Either you build Humble from source in your workstation itself, or the other option is that you can use Docker containers provided by OSRF, which have like the Humble desktop installation with them. So you can just straight away pull in those Docker containers, and you should be able to have a container which has Humble ROS to Humble running in that container, and it will be able to interact with ISXM, which could be running again either in the container or bare bones on your workstation itself. So for installing ROS, yeah, the best places to get started is you should follow the instructions as is, and this is for ROS to Foxy, where you can directly install it. You don't need a source installation if you're on Ubuntu 20, like I just said. So you should be able to follow all these steps here, and once you have like the demo nodes working and you can verify that ROS installation is correct, I think you should be good to go in terms of using the ROS to bridge with ISXM. And you can also follow the same steps for ROS 1 as well if you were looking to install maybe Melodic or Noetic. That's entirely up to you. So I think, yeah, in terms of understanding, so this is the OB launcher which we have. Let's go ahead and launch Isaac Sim from here. And I've already opened it in the file browser right here. Let me open up a new terminal and I'll be running Isaac Sim from the terminal here. So we can start Isaac Sim up by just, yep, so I've started Isaac Sim. The first thing I want to show is how you can enable the extensions for the ROS 1 and the ROS 2 bridges. And once you do enable those extensions, you can see like the corresponding Omnigraph nodes come up for those extensions. So in your ROS workflow, you'll probably be using various nodes in terms of Omnigraph nodes, like publishing images, subscribing to twist messages, publishing laser scans, uh, maybe publishing odometry. So all those nodes have been given to you with ISACSIM with with the extension itself. And when you do start up the extension, you should be able to see those corresponding nodes. And we'll be taking a deeper dive into looking at what the input for the nodes are and how you can use them. Yeah. Mm, wait for a sec while this loads. So the extensions can be enabled through the extension manager which we have, and one important thing to keep in mind there is you can only have either the ROS 1 or the ROS 2 extension enabled at one time. So uh, if you try to enable both of them at the same time, let me run that again. Okay, oh, it was compiling for the shaders. Apologies for, sorry about that. It might take a minute or two for the shaders to compile, and we should be able to have Isaac Sim running. Let me give you a quicker overview in terms of what's happening when you enable the extensions. So you have the ROS 1, ROS 2, and the ROS to Humble bridges available on Linux. And by default, we have the ROS 1 bridge enabled, and that's what is selected when you start up ISACSIM. However, you also do have the option of using a different uh, version of the ROS bridges, which are provided with ISACSIM. So a way you can do that is we can open up the base kit file, which is right here, and let's go ahead and look for the ROS bridge. I think we have it open right here. So this is the default bridge, which is enabled on startup. So it's the ROS 1 bridge in terms of your platform being Linux, and if you're using a Windows system, then you don't need to worry about having the ROS 1 bridge enabled by default because there's no support for ROS 1 on Windows right now. And We have a ROS2 beta version for the bridge, which works with Foxy, so you can give that a try. But for Linux, the default version which will be used is the ROS1 bridge. And in case you find that your workflows are centered around ROS2, what you could do instead is make sure that you change this maybe to, you just need to set it to the ROS2 bridge and you should be good to go. We'll keep it as is for right now. Meanwhile, let me take a look at a few of the questions we have here. So does JetRacer and the Isaac Sim drone use ROS? So I can understand the JetRacer is something which we have in terms of a robot which you can have the ROS nodes added to. So you have the wheels. If you want to add a camera and a lidar and other sensors, what you can do is make sure that you add those sensors and you rig up the corresponding ROS nodes for those sensors. So once you've done that, you should be able to have like a ROS version of the JetRacer, and now you can have your own software packages running from ROS which can control and do stuff with the robot. The other thing which you can also do is it can be independent of which it could be ROS1, ROS2, or ROS2 Humble. That's entirely up to you which versions of ROS you're using and which stack you will want to integrate with Isaac Sim. So how can we verify that ROS2 is running? Okay, that's a good question. So uh, if you want to verify that ROS2 is running, uh, so the fundamental difference between ROS1 and ROS2 in terms of using the extension manager and enabling the corresponding bridge is that for ROS1, you need to make sure that you start up ROS core. Let me open up the documentation right here. Mm, mm, So this, yep. So right here we talk about the importance if you're using a ROS1 based workflow where Isaac Sim by default will not start up ROS core. So if you are running ROS1, for example, and you hit play in simulation, and once you've done that, you have all your ROS1 Omnigraph nodes, which may be publishing like images, laser scans, or other things, but won't be able to see them unless you have ROS core started up in your own terminal somewhere else. So, and you can set the IP, the master IP for the ROS1 master, such that if you have it running maybe on a different machine or you have a distributed workflow, all those are possible. But whereas for ROS2, you don't need to start ROS core. There's no ROS core for ROS2. So what you would need to do in that case is make sure that you don't source ROS2 from the terminal which you're running IsaacSim from. I'll get into what happens when you try to do that. I think we should almost be done with the shaders being combined. I'll get into more details of what happens if you source your ROS2 installation before running IsaacSim. You have conflicting namespaces and it will crash. And it might not just open up the bridge itself. So we've mentioned that in the documentation too, where you need to be careful of not sourcing your ROS2 terminal when you run IsaacSim. And this doesn't apply only for like running IsaacSim from the GUI, but it also applies if you're running IsaacSim headlessly, for example, via Python scripts, and you're trying to enable the ROS2 bridge. So how can you run IsaacSim headlessly? Let's open up the same folder which we have, and we look at the standalone examples. We can now open up the Isaac ROS2 bridge, and we'll take a quick look at what happens there. So this is a simple subscriber with which has been written with ROS2, and you'll be seeing that how it can be integrated with IsaacSim and how do the callbacks work, how do you control steps in simulation and corresponding things. So the first thing you need to keep in mind is you make sure that before you make most of the Omniverse inputs, you need to make sure that you started a simulation app because all of those all of the headers, the libraries, and all the other tools which you might be using with IsaacSim will only be found after the simulation app is launched. So once you've launched the simulation app, we are sort of selecting which bridge we want because it's a ROS2 example. You have the example option of using maybe the default ROS2 bridge, which is ROS2 Foxy, or you can also use the Humble bridge. So once we've done that, we're going to import all the other things which are needed. So we'll enable the ROS2 bridge, And after enabling the ROS2 bridges, when we can import RCLPy. And RCLPy will then allow us to describe the nodes. We can write our own custom nodes as well. And we'll be using a string message from here, or even an empty message, a string message, or anything. That's totally up to you. The standard messages are all supported with Isaac Sim, so you should be able to use them. And yep, this is how the subscriber is. So you'll need to have the timeline. So the timeline is basically responsible for making sure that you can hit play in simulation, and you'll see that with Isaac Sim, for all the ROS nodes which you would be using, they won't execute until you hit play in simulation, because all of them sort of depend on playback tick, and that playback tick is only executed once you hit play. So you need to make sure that you have access to the timeline when you're running Isaac Sim from Python, and you hit play, so you can have your complete action graph set up with all the Omnigraph nodes for ROS, and it'll only start publishing and subscribing to data once you hit play. So that's why you need the timeline interface. We'll just define a simple world. We'll add the ground plane, and we'll add a prim to it, a prim called a cube, and we'll create a subscription right here. So this is the part where we can see that the ROS stuff comes into the picture, where we're going to create a subscription for this corresponding node, and the message type is just a standard message, and you can have it set to anything. It could be like an image message type or a string or anything. That's totally up to you. And you also have a corresponding callback for the subscribers, and that's something which you have defined right here. So the callback is called a move cube callback, and what happens there is it's just going to check if the world is playing, and then it's going to randomly set the position of the cube. That's all it does. And this is where you run simulation. So uh, once you've run simulation, like I just said, you need to make sure that you're playing the timeline. So once you play the timeline, now all the ROS components are activated. The publishers, subscribers, all of them should be working, and then you need to spin it so that the node actually receives the callback corresponding to the message type which is attached to, and you can continuously keep doing that in the loop. And once you're done, you just clean up, and that's so. This is a very basic example of what's happening if you want to use RCLPy based nodes or any ROS2 nodes with IsaacSim. So now we have IsaacSim up and running. Let's go ahead and I'll quickly show you what it means to enable the ROS bridges. So if you go on, if that was too quick, you can go under Window, Extensions, and you can look up for ROS right here. We have a ROS bridge, we have a ROS2 bridge, and we have a ROS2 Humber bridge. So by default, like we just saw earlier, the ROS bridge is enabled, and let's go ahead and see if we can find any of the ROS1 nodes which we would be interested in. So we can do that by going to Visual Scripting and Action Graph. Once we open up an action graph, we can take a look at, I'm just going to type in ROS. So this is all the corresponding ROS nodes now showing up. So you can look at this node called subscribe to us. Let me create a new action graph and show you what that means. I have a new ROS node called subscribe twist, and that just subscribes basically to your command velocity topic in ROS. And it's going to subscribe to that, and then the output from that node is going to be angular velocity and linear velocity, which it's received from the message itself. And you can pass that downstream to other nodes in Isaac Sim, and that will enable you to sort of control your robot, for example, where you have a teleop twist maybe running from a ROS package, and you have a corresponding representation of an Isaac Sim robot which has the action graph rigged up correctly. You should be able to move the robot, and that's something which we will be seeing in a few moments down the line. So most of the workflow which we'll be looking at is very similar for ROS1 and ROS2 in terms of how the action graphs would be set up and how you can bring your own stuff into Isaac Sim for ROS workflows. I'll be talking more about the ROS2 stuff, but the only thing which you need to keep in mind, it's almost identical for the ROS1 stuff as well. So Excuse me, let's go ahead and enable the ROS2 bridge. I'm gonna enable the ROS2 bridge. And we also had a quick question before, and we asked that someone's asked, Z has asked about how can we verify that ROS2 is running. So I'll give you an answer in terms of how that can be understood. So we've enabled the ROS2 bridge, and let me open up a ROS2 terminal as well. So let me source my ROS installation. So I have Ubuntu 20, so it's a Foxy installation. I'm going to source that. Okay, so yeah, ROS2 seems to be working. There's nothing happening because I didn't specify any command after that, but we have ROS2 running here. We've enabled the ROS2 bridge in IsaacSim. And let's quickly open up maybe a navigation sample. So the reason I'm showing a navigation sample here is because all of the ROS action graph has already been rigged up for the Carter robot so that we can have all the corresponding ROS topics being published to. And if you hit play in the sample and you see that you aren't able to understand if the topics are showing up in a ROS2 terminal, then that is where you'll probably understand that there's something either happening wrong in the action graph itself, or that there could be another issue. So we'll walk through a couple of them, and I hope that you'll be able to understand that better. While we're waiting for the scene to load, let me look at a few other questions which we have here. Okay, we have a question of does Isaac Sim come with a library of common environment assets like models of trees, people, and so on? Yes, so uh, we do have a lot of assets which come with Isaac Sim, and after going through the sample, I'll quickly show you where it is. But if you just want to look at it quickly, we can actually do that right now. So if you go to your local host, one which should be installed once you've sort of installed IsaacSim, you've installed Nucleus and Cache. Installing Cache is recommended because once you have Cache installed, what that enables you to do is it'll load up your scenes faster. So especially with more complex scenes where you have a lot of objects, you wouldn't want to wait for a while before the entire scene loads. So having Cache enabled really helps there. So let's look at the assets which are already provided. So you have all the NVIDIA assets right here. The ones which we would be interested in are going to be the Isaac assets. So it should be on your local host itself, and it's this path right here. Let me put that in the chat, and should be able to look at that. So this is what your asset path would probably look like. And once you've installed Nucleus and you have all the other dependencies good to go as well after you've installed IsaacSim. So once you're here, you can go ahead and look at all the samples which are provided with the IsaacSim assets. So you have a bunch of robots. You have the Carter robot, you have Jackal, you have Fester. So you have manipulators, mobile bases, AMRs, you've got the collection of all of them. Also have simple model for vehicles and other assets like forklifts, which you could use. So this is where, so someone asked about the jet racer. Yes, you have the jet racer here as well. You can go ahead and open it up. And because today we're particularly focusing on the ROS side of things, for the ROS samples, you can go to ROS1 or ROS2. You have scenarios over here. We have the navigation scenario, which is just opened up right here in front of us. And we also have robots which have the ROS action graphs rigged up for them. And the Carter robot right here is the one which is going to be dragged in from here to here. So let's get back to the ROS side of things. So what I'm going to do now is I'm going to hit play. So this is a sample warehouse scene which comes for the navigation example provided with IsaacSim. You can see like we have a couple of forklifts right here in the warehouse scene. We have a Carter robot, and we can open up that robot and see what the components are. We have the chassis, we have the wheels for the Carter robot. So if you closely look at the Carter robot, we can even go and take a look at what the Carter robot looks like. So you have the left wheel, you have the right wheel, you have a LiDAR on top over here, you have a pivot wheel right here. So it's not actuated, the wheel which is at the back of the robot. The ones which are actually controlled by the motor are the left and the right wheels. and you also have a real sense camera right ahead over here. So it's a stereo camera. You should be able to get depth information out here as well. So this is what the Carter robot looks like visually, and I'm not going to open up the action graph because it might look overwhelming to someone who's going to look at it the first time. But we'll break it down and we'll be able to understand what's happening at the lower level. So just to understand what's happening here, let's go ahead and hit play. So what's happened here is we've set the default camera for our scene to be the Carter's camera. So the view which you have right here, the viewport window, has now been attached to the Carter camera, the stereo camera left. So now let's see if things are showing up on the roster side of things. So we should be able to see. So here you saw that we can't see any of the topics showing up, and because this is the navigation scene, you would expect to see all the topics showing up. So if you open up, let's quickly look at what is the information. So in navigation, so there's a lot of things happening in general for navigation sample, but when you do run navigation sample, you should be able to see like the map, the lidar scans, the transformations, and all the components showing up. So what's happening here is there's nothing which is coming up. So that's one of the issues on the ROS2 side, where you need to make sure that the middleware, the DDS framework which you're using, is specified correctly, and we've not done that. So because of that, what's happened after we've hit play is we've seen that nothing has shown up on the ROS2 side of things. I won't be able to interact with the robot in any way with any ROS2 commands because ROS2 doesn't know that there's a robot right there, and that's a problem, obviously. So the solution to that is, let me hit stop. And if you look at the documentation right here, this is an important step which I wanted to highlight. You need to make sure that you're setting your fast DDS config right here, especially when you're having any ROS2 based workflows. Because what that allows you to do is it makes sure that your simulated robot or any simulated ROS graph which you have is able to be found with ROS2. So let's go ahead and make the change right here. So we'll have to quit sim. Let's do that. I'm gonna just quit sim. I'm going to unset the exact instructions which I'll follow, and export this default profile file, and equal to. So this file is also provided with your ISAXM installation itself, with the ROS2 installation. It's right here in the fastdds.xml file under your ROS2 workspace. So let me, if you want a visual representation of that, that can be. So your ROS2 workspace has the same fastdds as XML file which we're just looking at. So going to make sure that we set our fast RTPS default profile to that, and we're going to run ISAXM again. So what this will enable us to do is now we'll see that the topics and all the corresponding things which are being published and subscribed to from the simulated robot side of things actually show up with the ROS2. While we're waiting for this to load, let me see if we have other questions right here. So I hope I've been able to answer the question on the library with common environment assets. I might give you a quick walkthrough of what are SIM-ready assets, because I think someone has asked. So Z has asked the question: do assets bought into ISAXM need to be SIM-ready for physics to work properly? So that's a good question. So it uh, it really depends in terms of how you're bringing in the assets. So if you're looking at it from a robotics viewpoint and you have your ROS stuff set up, so you might probably be having like a URDF representation of your robot. So we'll be looking at what the URDF importer is in this session, and how you can bring your robot in from the URDF importer. And what that allows you to do is set up the physics by default, and that can be very helpful because then you would not need to go and manually define joints and all the other information to actually rig up your robot with physics so that you can control it. So we have some opened up right here. Let's go ahead, do the exact same thing which we did before. We'll enable the ROS2 bridge and we'll open up the navigation sample. So for sim-ready assets, it really depends on how you want to use Isaac Sim in your own workflow. So if you're looking for advanced AI workflows where you only want the visual side of things, where physics might not matter for you, but as long as objects are visually represented well, that's good enough for you. So, uh, but if you want to, for example, simulate a robot and physics is important to you as well, and maybe visualization is not as important for you, so it wouldn't really matter if the Carter robot looks like this, or it could be any robot, it could be your robot, but it doesn't need to have all the material textures and all that stuff set. And you just want to make sure that the physics is correct. So SimReady depends on sort of what your use case is in terms of simulating physics only or just the visuals or both. uh, the assets which we're going to use right here, the default ones which are provided with Isaacson usually have the physics and the visuals enabled with them. But when we'll be going through the erdif importer, we'll sort of import a turtlebot, and you'll see that you'll have good physics, but for the visual side of things, you might have to add the materials and textures yourself. So we'll be able to take a detailed look at that next. So let me hit play right here, and let's again. Okay, so this is good news. So now we are able to see all the information which is being published out from the simulated robot actually show up on the ROS side of things. So we have various things coming. We have the transformations being published. We have a laser scan. We have the image from the Carter left stereo camera. We have the odometry. We're subscribing to command velocity because obviously navigation will be sending velocity commands, and clock and camera info too. So this looks good. Let's check if we can actually see this in Harvest. So I'm gonna go ahead and open up Harvest right here and minimize this and maximize this. Okay, so let's set our fixed frame to be odom. Just another pointer in general, if you're new to ROS 2 and transforms frames and all in general, it is usually important to make sure that your fixed frame is correct because many of your messages or information is mapped to corresponding frames when they are being visualized. So for example, laser scan is being published actually from the Carter LiDAR itself, but when it's moving the robot and is being passed to the navigation stack, there's a whole transform tree corresponding to the base link, the odometry frame, and the camera transform, the LiDAR transform. All of that is being passed to the navigation stack. So just to summarize it, make sure that you set your fixed frame correctly, and let's let's see if we can. Oops, let's set our topic correctly. So we have all the options for. Okay, so we can see the RGB image corresponding to the Carter robot visualization now show up. So for reference, this is what the Carter robot is seeing, and this is what is being published over from the ROS side of things. And once you've made sure that you fix the fast DDS middleware and you've started up Isaac Sim with the ROS2 bridge enabled and open the navigation sample, you should be able to see this. We'll add visualization for a few more topics right here. So we can go ahead, add for laser scan, and let's set the topic to scan. So right here, now we can see that the LiDAR information from that map has started to show up too. And we also want to understand where the robot is. So let's add the visualizations for the transforms too. So this is what the transform tree for the robot looks like. And we actually go in here, should be able to see all the frames. So we talked about the frames, the right wheel, left wheel, odometry frames, the IMU, LiDAR, Carter camera, all of them, and even the tree visualizations. You can even have the names show up here. Seems to be a little messy because you can't read what's here, but in general, it's sort of giving the visualization of all the frames present on the robot and the corresponding names and relationships. And let's see if we can tally up the robot. That's a simple test. And let me open up, source my ROS installation again. We have sourced. I'm gonna run tally up twist. Okay, tally up twist open right here. I'm gonna see. Okay, the robot seems to be moving. Yeah, you can see that the odom frame and just spinning the robot around right here, and it's doing the same in Isaac Sim. So your robot information, all the transforms, the laser scans, the images, everything is being put over to the raw side of things. And from the raw side of things, I'm just spinning up a teleoptwist keyboard node, which is controlling the velocity of my robot so that I can actually move it around. So this sort of gives you a preview of how you can integrate your own workflows maybe with uh, with ROS if you want to use Isaac Sim along with that to simulate your robot. So I think this was a good preview to understand. We will be taking a deeper dive into what's happening under the action graph and a lot of stuff going on there. So the other thing which you want to keep in mind is you do not want to source your ROS to installation when you before you run Isaac Sim. So let me show you what happens if you actually try to do that. I think um, the easiest way to understand what's happening there is to actually go ahead and make that mistake. So let me, so here I don't have my ROS to workspace sourced right now, but I'm going to go ahead and source that. I've sourced my ROS to workspace. We have a few questions right here. Um, How should we think about organizing USD for our bots, especially creating them from scratch? That's a good question. So I think we have a good tutorial for actually doing that from scratch. It's an advanced forklift rigging tutorial. It's called the robot import. So rigging robots. So this is a little bit of an advanced tutorial which is going to talk about all the steps you would actually need to go through if you have nothing set up for your robot. You just have a USD or you've gotten it from a 3D CAD importer, and now you're trying to make sure that you have the right physics and the nodes correspondingly set up. So it's an iterative step-by-step process in terms of which you need to first identify the joints in your robot. Once you identified the joints, you need to understand your joint is probably going to be attached to two bodies. So if, for example, it's a wheel, you would need a revolute joint between the wheel itself and the robot. So you need to go ahead and set those up and make sure that the axis of the robot wheel and the robot match correctly when you're rigging it up. And for any objects which you would want to move together, you need to make sure that they are actually in the same transform. So, for example, the forklift body, you would not want that maybe the chain, which is a part of the forklift, remains behind when you're actually moving the forklift. So, in order to make sure that you have that behavior, you need to make sure that your transforms for the robot is set up correctly. You need to organize the hierarchy. Once you've organized the hierarchy, you'll need to assign collision meshes for the parts which are going to interact with each other. Once you've added collision meshes, you've added the transformation hierarchies, and you've added the joints, you should be good to go. So let me paste the link for that right here. So this is the tutorial which is the one I'm referring to right here. So if you want to rig your robot from scratch in Isaac Sim, if you don't have any representation whatsoever, maybe you just 3D modeled a robot, you've not tried ROS as well, and you just want to understand how you could actually simulate it in Isaac Sim, this should be a good starting point. And if you have already used URDF representations before, so there is a simpler way to actually have the physics rigged up for your robot, and we'll be looking at that. So let me stop the showing. Yep. Okay. So let's I've sourced my ROS workspace right here, and now I'm going to run Isaacson again. So what happens when you source your ROS workspace and when you try to enable your ROS to bridge? So you won't have any problem if you're using ROS 1 because for ROS 1 sourcing your workspace does not have any impact on how the bridge extension is loaded. But for ROS 2, they are conflicting names in the libraries which are being loaded, and that's going to cause errors when you try to enable the bridge. and that error can be a little difficult to debug because you might see that maybe uh, simulation is complaining that you have Humble bridge sourced, and you would be like, I don't even have Humble installed. How can I have Humble sourced if I don't have Humble installed? So let's go ahead and actually enable the ROS to bridge. We'll keep a close look at the terminal right here as well in terms of what happens. I'm going to disable ROS1 and start up ROS2, and I get an error. Okay, it's not able to start the ROS2 bridge. It's failed to acquire the interface, and it thinks that you've loaded the Humble bridge as well. So give a quick insight into why this has actually happened. So the answer actually is related to what happens when you source your ROS workspace. So when you do source your ROS workspace, it adds all the ROS dependencies in the environment variables itself. So let's stop simulation right now. Nothing is going to happen. So let me hit export, and you'll be able to see what actually happens here. So this is an important variable right here, LD library path, and you'll see that it's now loading the libraries from your default ROS installation. And because of that, what's happening is IsaacSim comes with a version of ROS compiled with it because we have other dependencies like Python 3.7, and we provide a ROS compiled version with IsaacSim. If you try to source your own workspace and actually get in the libraries from there, what happens is the the ROS which is compiled with IsaacSim versus the one which you already have installed, they have conflicting names, and because of that, it won't be able to start up the ROS to bridge extension itself. So if you do not source your ROS workspace, so usually when you see errors related to this, where even just starting the bridge gives you problems, you would want to make sure that you aren't adding any default source messages. So because I know like the ROS installation itself gives you instructions of adding it to the bash RC. So so you can they usually instruct you to add this to the bash RC itself where it sources your ROS workspace, and that makes it more convenient when you're using ROS. But what happens because of that is all these libraries are already set through environment variables, and they conflict with Isaac Sims ROS version, and that causes problems when you try to start up the bridge. So a quick pointer, if you're not able to load any of the ROS2 extensions because of issues related to maybe like the one which we just saw, that there was a null pointer for the extension itself, and maybe complains that there's a conflicting library or it can't find a library, the most probable reason is that in some way or the other, something from the ROS installation which you've done is being sourced before you're running IsaacSim, and because of that, you're seeing the conflicts and the bridges not being able to load. So the best way is not to source your ROS2 workspace before you run IsaacSim. So let me go ahead and just quit this terminal. I'm going to start up a new terminal right here, and make sure I do the fast DDS steps, because otherwise we would have to spend a few more minutes there. So, and when you actually hit export here, you will see that nothing of the Foxy side of things actually show up. So there is an LD library path variable, but it isn't tied in any way to the ROS installation. So loading the ROS bridges itself does not give you any issues when you actually have uh, when you actually don't have your ROS workspaces sourced. So I'm just going to follow the instructions as is, and we'll set our fast RTPS default profile to this. So we're good here, and I think we can now get into how you can use action graph and the URDF importer, and how you can actually bring your own robot in for Isaac Sim ROS workflows. So I have a few samples which I'm planning to run through for that, and I hope you'll find them useful. We have any other questions? Okay, how Qt can make our virtual humans in Isaac Sim, not graphics, but fundamentally. Okay, so I think this is we do have samples in terms of using human assets with Isaacson. Let me open up the documentation right here where you should be able to find that. It's called the people anim extension. Yep, right here. So this is the anim people extension, which should be your reference in case you're looking for simulating humans with Isaacson, and you can have these human USDs set up in ways which you would want to. So you can add animations to them. So for example, they could be walking, they could be standing, they could be waving, and you can Python script them to actually move around on the floor. You can have them navigate around in an environment. And you should be able to follow these instructions as is to get started with uh, how you can use the people assets with Isaacson. Yeah, the default pose which they do come in is with the T pose, but as soon as you hit play and you've added a corresponding animation to it, you should be able to see that the position changes and have all the instructions for using people assets, and I can paste that in the chat too. So I have that for reference. This is the link I'm talking about, the anim people extension. You should be able to find all the related documentation right here. And if you have additional questions or further problems, please reach out to us on the forums. We're active there and we'll help you resolve the issues. Okay, so let's get back to our ROS workflow related stuff which we're looking at. So I was talking about the URDF importer. So let's see what that is. Let me first go ahead and enable the ROS to bridge. I'm going to enable the ROS to bridge, and not going to go through Isaac examples now, don't worry. We'll go through a URDF importer. So this is the URDF importer which comes as a part of Isaacson, and you should be able to use this to import your URDF and get it into a USD. And while doing that, what it's going to do is make sure that the physics and all the inertia and other properties which you've defined in your URDF itself get mapped to their corresponding versions with OV and Isaacson, and you should be able to use it directly. So I think Turtlebot is usually a good starting point in terms of understanding how it works, and that's the one which is a part of our documentation too. It's going to be similar to this, and let me just first find the file. It should be Turtlebot, Turtlebot, Turtlebot description, URDF, and we'll use the burger. So this is the URDF file which we'll be using. We'll select it, and a few things you need to make sure when you're actually using the URDF importer to have these parameters which are described are set up correctly so that it's imported correctly. So because it's a mobile robot, you don't want to fix the base link. Obviously, when the wheels of the robot would move, you would expect that the whole robot moves. It shouldn't be fixed. So make sure to uncheck that option for mobile robots. And it's going to be a velocity drive. We're just going to control the velocities of the wheels via command velocity and from the ROS side, and we should be able to use it. So to explain, let me create a simple create a grid room, for example. This is our grid room environment right here. And let me import the Turtlebot here. So it's popped up. It's here. This is our Turtlebot representation right here. So as I just mentioned, and we had a question in the chat too, that because we've used the URDF importer and the meshes and the textures are not defined. So we have the meshes as a part of URDF, but the textures and materials aren't defined. So this is like the standard representation you would get when you get in get in a robot from the URDF importer to Isaacson. If you have importance for the visuals as well, you can add materials and the related components to parts of the robot. So we can have like the wheel maybe having a material like rubber, and we can have plastic material set up for this, and we can set their colors so that they look visually accurate. So that is something which you could do, but we're just going to focus on the raw side of things, and for that we just need physics to work correctly. So that's what we'll be looking at. So let's quickly look at what the hierarchy looks like for our robot. So we have the base link, we have a back link, we have two wheels on the left and right, and we also have the lidar up on top. So this is what your turtle bot would be looking like when you get it in via the ERDIF importer. And hopefully when I hit play, things look fine. So yep. So as soon as I hit play, because I use the URDF importer, the robot came into the USD format with the right physics. And what happens is when I hit play, the physics scene is already added. You can see that the robot now drops down to the floor. So that's not very clear. I can maybe shift the robot up. Should be able to see it drop down to the floor. So looks like the right physics is probably set up for the robot. And now what we want to do is, can we set up an action graph so that we can actually control the robot? So just like we did for the Carter robot, what are the steps I would need to go through so that I can actually now control this robot which I've imported via ROS? So let me go ahead and open up a file which we have to actually help with that. So the file which I'm about to open up, and it's just the same turtle bot in a simple room environment, and I've set up an action graph which will actually control uh, the robot itself via ROS2. So this is the same turtlebot robot which we just looked at. It's in a different environment called the simple room, which is like one of the standard environments provided with Isaacson. It's the hierarchy, everything is the same. The only addition which we have here is a component called action graph. And if you aren't familiar with action graph and this seems to be a little bit out of the world for you, let me give you a quick starting point in terms of how you should look at action graphs to get started with. Not this one. Controller. Import robot. We're looking for importing a robot. Okay, this is talking. Core API, assemble, simple robot. There was a chatbot tutorial for actually driving the robot. Let me see if I can find it from the ROS tutorials down here. Assemble simple robot. Apologies for that. I think it took me a while to find it for the documentation. So I think yes, this is a good starting point in terms of understanding how you can set up basic physics for your robot. And the example right here just talks about having a basic body and two cylinders as wheels, and adding the correct physics to it and the hierarchies to it. And the other thing which you can actually do is also add the ROS parts to it. So let's look at that in more detail. So let's open up the action graph right here. So this is what our action graph looks like. So the important node here is the ROS to subscribe twist node, and this is going to subscribe to the command velocity which is being passed from the ROS side of things. I'm subscribing to the topic name which I've set right here, and can also set in other parameters like queue size, and I can set up context as well. I can add namespaces which will sort of prefix to the topic name so that you are subscribing and publishing to the right messages. Then once I am subscribing to this message, I'm just getting the angular velocity and linear velocities from here. The angular velocity is passed because we have two-dimensional motion only. The robot will be moving along the ground plane itself. The angular velocity is only going to be about the z-axis. It's going to turn, and the linear velocity is going to be around the x-axis where it's going to move. So I'm just going to set up my other components in the action graph corresponding to that behavior, where I'll get the angular velocity vector, I'll break it, and I'll only use the z component of it, and I'll pass it in as the angular velocity to my differential controller. So the differential controller is going to do is going to set is it's basically the parameter which allows you to uh, move your robot and set the velocities corresponding to the wheel velocity. So it's mapping the wheel velocities to the robot velocity. And I'm going to do the same with the linear velocity. I just need to scale it before I pass in the x component of that linear velocity. I'm going to pass it into the differential controller, and the differential controller actually passes it into the articulation controller. And the articulation controller is responsible for moving the whole robot because the robot is treated like an articulation in Isaacson. So if that sounds a little new to you, I think it's mentioned even in the documentation right here, where setting up a simple robot has the component of adding articulations to it. So once you've done that, you need to specify the joints which are actually going to be controlled via your robot, via the messages itself. So we have a left wheel joint and we have a right wheel joint, and we can see those joints from here. We go to the base link and let me expand that. So we have a left wheel joint, which is the revolute joint for the left wheel right there, and we have the right wheel joint. So at an overview level, what's happening is you're subscribing to the messages coming from the ROS side of things. You're making sure that those messages are being pre-processed and sent to your robot, and your robot joints, which actually need to make sure that the robot is driven corresponding to those messages, are actually being passed into the controller. We set all of this up, and so you'll notice that your ROS nodes and almost all ROS nodes depend on your tick, which is the execn, and that only is triggered when you hit play. So if I do a ROS to topic list right now, there's nothing showing up. There's no topic which is coming up here because I've not hit in play, so nothing will be showing up. So another thing which you would also want to keep in mind is make sure that you're hitting play in all your simulations when you have any ROS related components in your workflow, because those get triggered only when you hit play. Let's hit play. Okay, and see ROS to topic. Oh, I can see a CMD well now come up. So this is the subscriber which is being spawned by this Omnigraph node right here. And what that subscriber is doing is subscribing to twist messages, and it's going to now move the robot corresponding to that. So let me go ahead and start that up. So we have teleup twist open right here, and I've hit I. So that's basically moving the robot ahead, and you can see that the robot has now started to move ahead. I can turn the robot too. So in order to actually understand if the stuff from your raw side of things is making it to the robot, look closely at the subscribe twist message, and you can see the outputs change when I'll actually change uh, the the subscribe message from the teleup twist. So when I do change that, you'll see it's changed to 1, 0.5, it's changed to -1, 0.5. So it'll keep changing when I actually hit the corresponding nodes to drive the robot. And once that happens, you'll see that the corresponding values and the velocity commands keep changing as well too, which actually ends up driving the robot. So the velocity commands keep changing as I am hitting those keys, and which inherently then actually drives the robot. So this is a simple example of understanding how you can subscribe to a certain message type and pass it into Isaacson so that you can actually control your robot via ROS. And let's look at a few quick simple examples as well, to actually understand different nodes which we can look at. Let me just quickly hop over the questions as well. How do I connect a LiDAR of robot vacuum cleaner on the Jetson Nano? HSI score. I'm sorry, I'm not sure if do you mean like in the real world or in simulation. So if you're talking about simulation, you can do that easily. You create the LiDAR itself. Once you've created the LiDAR, you can add it to the corresponding place on your robot, and when you hit play, that LiDAR is going to be simulated. And if you want to have the raw side of things actually show up, so that's something which I'm going to show you right now. So let me go ahead and create a new stage. You create a simple stage of a grid room, and let's add a camera here. So this is the camera right here, which is shown up. I'll also add maybe a cube to the scene. A cube. Let's shift our perspective to that camera and see if we can actually see that cube. Okay, we can actually see it. Let's move a little bit higher. So this is what our camera is currently looking at. Now what we would want to do is we want to make sure that the images which are actually coming in through from the camera, can we stream it over to the ROS side of things? So to do that, we just need to set up a couple of Omnigraph nodes which are going to publish the information over to ROS. And once you've done that, you should be able to see those visualizing up and on this. So let's create a new action graph. And first node we will be needing is called create render product. And we will need a ROS2 camera helper. Focus more on the action graph and a playback tick. We have playback tick. These are the only three nodes you would be needing. So create render product is basically going to make sure that corresponding to a certain camera, all the rendering information which is being processed by that camera is being passed over. So uh, it will give you the corresponding path to that render product, and that's what is going to be the input for a camera helper. So let's get started in terms of connecting our connecting our action graph. So we'll connect the tick to exec in. We need to add our camera. We add the camera which we just made right here. I'm going to add it. I'm going to make sure it's here, and I'm going to connect the render product path to the render product path for the camera helper. So these are the only values which we would probably be needing, but we can take a look at what the other options are. So the frame ID is the sim camera. If it's something you want to change, and we saw in the RViz example earlier why it matters. So if it is something you want to change, make sure you do change those values. You can set up node namespaces. You can set up ROS context as well. The render product path is being computed and set. So when you see an equal to sign here in the Omnigraph, that is usually when that node is being, the value of that uh, input or output for that node is being set by another node. So for the other nodes, if you'll see, there's no equal to sort of symbol showing up, but for this node, you'll see that the render product path is being computed from this node right here and then connected to the camera helper node. We want to publish RGB information like the images itself, and the topic name can be RGB as well. So we just need to go ahead and hit play. We hit play and see if the topic is shown up here. So I can see the RGB topic has shown up here. I can also do an echo of the topic. Usually echoes are not useful for images. We will have an RViz visualization open up too, but just see what's happening. So this is the entire image info being sort of published over to ROS, and the data won't make a lot of sense because of the way it's just numbers and no understanding in terms of what's happening. But the frame ID, the one which we set in simulation, the height width of the render product. If you want to publish images over a different resolutions, you can just set the height and width in the create render product to those values, and you should be good to go. There aren't any other changes you would need. So encoding is fine. Let's open up RViz and see if we can see the image. So you can see the image now popped up right here. It's the image which the camera is looking at, and let's go ahead into the camera stream and see what's happening. So we have this is the image right here, and let me see if I move the camera around, and yep, you can see the same info is being published over to RAW. So the camera has the images which are being streamed by the camera is being continuously sent over to ROS, and as the camera moves, I can see that the messages even on the ROS side of things have changed. So this is the behavior you would expect. And I hope that answered the question of how can we extract frames that the camera sees by Zia. And this is how you could do it via Omnigraph with the ROS to camera helper nodes. And if you want to use a Python-based sample for it too, so the exact same steps which we've done for the Omnigraph via the UI can also be done by a Python script. And we're going to see that for a LiDAR as well. So I'm going to create, again, the simple environment. room which we had, and we'll create the grid room. And let's create a new action graph. And now we're going to do the LiDAR example instead of the camera example. So we'll use the RTX LiDAR. So it's let's create the RTX LiDAR first. So go under Isaac, sensors, LiDAR. This is the regular LiDAR is a physics-based LiDAR, and you can use that too. I'll be talking about the RTX LiDAR example. For both of the corresponding nodes, we have ROS2 publishers, which will enable you to actually stream your laser scans and point clouds out from simulation to the ROS side of things. So let's create a rotating RTX LiDAR. It's here. Okay. And we'll add a few objects to the scene. I added a cone, a cube. Added a cone and a cube, and what we can do next is we'll create our action graph like we did just before. So we need a create render product node just like earlier, and we'll need a LiDAR helper node instead of the camera helper because we're going to be publishing LiDAR stuff out from here. And we need the playback tick. Have playback tick. Let's set it up. So let me set the camera prim right here, and the camera prim is the RTX LiDAR which we've just created. So you'll notice that the prim type is a camera. So the RTX LiDAR type is a camera type, but don't worry, the actual data which is going to be streamed from that is defined in the properties further downstream, and that's simulating the LiDAR sensor which we're interested in. So we're going to add that in here. The render product path needs to be connected to the render product path, exec out to exec out. Tick. So it's basically just the same Omnigraph node which we just saw of our camera helper node, and it's doing the same thing. Instead of the camera right now, we're going to publish over the LiDAR info. So you can look at the LiDAR helper node as well. The frame ID is sim LiDAR. You can set other ROS parameters as well if you want to. You're getting the render product path from the create render product node which we've just created. And you can publish either like a laser scan or a point cloud. We'll publish a laser scan on the topic name scan. So let's go ahead and hit play. And let's see what's happening on the RF side of things. Don't worry, that image is gone. It's not there anymore. We have no image. So don't have any image. Let's add my topic, laser scan. Okay. Need to make sure that the okay. So now we can see that uh, the laser scan is showing up for the corresponding objects which we have right here, and showing up here. So move it around, and you can see that the laser scan is showing up right here. So and you can also do the same thing for the point cloud, and if you see the boundaries of the entire grid room have also been marked. So this is how you can have LiDAR information being published over from the Isaac Sim side of things actually show up on your ROS based workflow. So we added a sphere into the scene, and we can see, oops, I think I went too high with that sphere. You can see that the sphere is now showing up too. I'll move it around, and the same visualization is showing up on the Isaac Sim side of things from the ROS bridge which we've just used. Let's go ahead and close this. I think we are almost running overboard, and the only last example which I wanted to walk through was I think we already saw initially how you can do all of this via Python scripts itself. So the example which we just saw for the RTX LiDAR, you can the steps which we just did from the GUI, they can be done from Python code exactly in the same way. So we just create an RTX LiDAR like we did from the menu itself. We are going to publish a point cloud and the laser scan. So we create writers for that, and we attach our writer to the LiDAR itself, and we just hit play, and it's going to publish things out from the Isaac Sim side of things to the to your ROS workflow, and you can sort of understand what's happening there. So all of this can also be done via Python scripting. And a couple of more things which I just wanted to go through before we wind up for today is so we have the ROS to bridge enabled, right? Let's go ahead and import RCLPy. So this is again going to be a ROS to specific thing, and I'm going to print RCLPy. So what this is going to do is it's going to show me the location of where RCLPy is being called from. So you can see that this RCLPy is being called from the extension itself. So this is the reason why you can't source your ROS2 installation before you start ISACSM, because then it causes a conflict between these two versions. So there we have our own version of RCLPy, and the ROS2 libraries compiled with Python specific dependencies for OV, and that is what is being used when you're actually using any of the action graph nodes for ROS2, and they are responsible for making sure that information is being published out to ROS and subscribed from ROS. So that's why you want to make sure that you don't source your workspace before you actually run ISACSM. And I think we can maybe wind up with the navigation sample towards the end, and I'm going to show the action graph which we have set up for navigation. I think we've already seen in terms of the basic understanding we've seen how you can subscribe to twist messages from the ROS side of things to move your robot. You've seen how you can set up LiDAR sensors and camera sensors to actually stream information out from simulation to ROS. And the only thing which navigation sort of adds on in terms of understanding what's going on there. So let's open up the action graph. See, there's a lot of stuff here. Don't get overwhelmed by looking at the graph. It's once I think we've understood what's happening at the basic level, it's pretty straightforward to understand what's happening. So let's look at the bottom of the graph first. See that it's a subscribe twist. It's the same as we did for the turtle bot, where we're trying to move the turtle bot with command velocity messages. So we just need to subscribe to the command velocity. And this velocity is being published over from your navigation stack. So your navigation stack understands where your robot is in the environment, sort of then tells the robot what the next velocities and paths are going to look like and sends it over to the robot. So you need to subscribe to that, and you need to actually make sure that the simulated robot behaves that corresponding way. It's doing literally the same things which we saw. We are going to scale, we are going to put it to the differential controller, and then we're going to send it to the articulation controller. So this is going to drive the robot. Now let's take a look at the LiDAR side of things. So that's straightforward too. We are going to read the LiDAR information. We just need to specify the LiDAR prim itself. We specify that the Carter LiDAR is the one which we want to read information from. And once you've done that, you just publish it over to ROS. So you read the LiDAR information for a corresponding LiDAR, and then it publishes it over to ROS. So you have your laser scan being published over to ROS, and you also have your command velocity being subscribed to. The only other thing which navigation stack needs is odometry and transform trees. So we have corresponding ROS nodes for that, and those have defined everything. We are publishing transform trees, the TF, which we saw earlier, the hierarchy of frames, so that that can be passed to the navigation stack for actually moving the robot. So this is what the action graph looks like at the overview. Also need time over here, so those that information is being read from ISACSM and correspondingly being sent over to the ROS side of things as well. Let's hit play, and I think the only thing which I not covered till now is uh, the ROS2 workspace which is provided with ISACSM. So let me go ahead and do that. So we have a couple of packages which are already available with ISACSM in the ROS2 workspace, and they're mainly around the navigation sample itself, where we have the URDF representation for Carter, and we have various navigation we have various navigation scenarios and maps correspondingly loaded. So we have the Carter warehouse navigation sample, which we will be looking at uh, in this tutorial. So let me open up navigation itself right here. ROS to navigation. So in order to understand actually what's happening in detail, I would strongly recommend you go through the documentation itself, and even if you open up the action graph and look through stuff yourself, I think it should make sense in terms of what's happening and why things are being done a certain way. So let's go ahead and start navigation. I would need to source my and start navigation. So I have navigation opened up right here now. So let me add the description file as well. Add the cart to UID, which just looks good. And this is what the navigation sample should look like once you've started up Isaac Sim. This is the robot view right here, and all the information, the laser scan, the map itself, everything has been loaded. Just set a navigation goal, and you should see the robot move. You can also add images, and you can have all that stuff streaming over from ROS as well. So this is how you can actually integrate your entire navigation stack from the ROS side of things, where uh, the laser scan, the velocities and everything have corresponding nodes with IsaacSim, which can be run and connected to your software stack. You can also do this with Move It. You can do it with your own cross packages. As long as you're able to publish to and subscribe to the information in IsaacSim, you should be able to do and simulate your robot in the way you would want it to. So I think this was all I had, which I wanted to cover for the ROS workflow side of things, and can wait for a couple of minutes in case there are any questions, or else we should be done. Start, and I can keep sim running if people have questions. Okay, I think we don't have any questions. So thank you so much for joining. I hope you found this session useful. And if you've been using IsaacSim or are planning to use IsaacSim in your workflows, I would strongly recommend following the live stream sessions which we have, because we've been discussing like various other parameters as well, like how do you set up sensors in IsaacSim, for example. We have sessions related to physics, we'll have sessions related to reinforcement learning, synthetic data generation, training of models. The ROS workflow is one side of things. So I would strongly recommend you would go through the sessions, and please reach out to us on the forums if you have any questions. In my session today, I tried to answer most of the questions around ROS which you've seen in forums, and I hope you found this helpful. So thank you so much for joining, and take care.